Hi, this lesson's on the definite integral. Okay, now a definite integral has a numerical answer, whereas your indefinite integral resulted in some function plus some constant. Here's an example: integrate 2x plus 5. Well, you should know that they gave you 2x squared divided by 2, which is x squared, and 5x plus some constant. Definite integrals specify values to put in place of x in that formula in 1. These are called the limits of integration, and we write them with the x values on the integral symbol like this. So let's do this definite integral, the integral of 2x plus 5 from 1 to 2. Those 1 and 2's are actually x values. Alright, so we would write the integral x squared plus 5x, and we'd put a square bracket and we'd put the 1 and 2 on the outside. You'll notice that there's no need for us to write c, because we're actually going to substitute the 2 and the 1 into that formula and then subtract the two answers. So those c's would then cancel. So let's do that. I substitute the 2 in first. Always the top number goes in first, the top number on that square bracket, the top of the integral sign. 2 squared plus 5 times 2, take away, open a bracket, 1 squared plus 5 times 1. Work out those answers. The first bracket you get 4 plus 10, the second one you get 1 plus 5. That's 14 take away 6, which is 8. So the definite integral of that function is 8, a numerical answer. Alright, so let's summarize. In general, if integral of f of x is equal to capital F of x plus c, some new formula plus c, if you integrate with a definite integral from a to b, x equals a, x equals b, fx dx, you will get a new formula, and you're going to substitute a and b into that new formula. The b goes in first. You get f, capital F of b. That's indicating that b has replaced x in the formula. Subtract capital F of a. Alright, a has replaced x in the formula. Right, let's do an example and see what a definite integral is all about geometrically. Right, so I've drawn the graph of y equals a half x plus 1. The y-cut must be at x equals 0. If you make x equals 0, you get y equals 1. So you can see I've made a 1 on the y-axis. X cuts at y equals 0. Put y equals 0 in that formula. You get a half x plus 1 equals 0. Half x is minus 1. X is minus 2. And I've made a mark at minus 2 and joined up the 2 points. I have my straight line graph. Alright. Now let's integrate that. Let's do a definite integral between 2 and 6 of a half x plus 1 and see what it means geometrically. Well, off we go. We integrate. We get a half x squared over 2 plus x, and that's a x squared over 4 plus x. Okay, divide a half by 2, you get a quarter. And between the limits 2 and 6. Substitute the 6 in. You'll get 6 squared is 36. Divide by 4, that gives you 9. And then put the 6 where the x is. You get 9 plus 6. Then substitute the 2 in. You get 2 squared, which is 4. 4 over 4 is 1. You get 1 plus 2. Okay, subtract those 2, you get 12. Alright, now show the lines x equals 2 and x equals 6 on that graph. Draw them. And let's work out the area enclosed by those lines, the x-axis and the graph. What type of shape is it? Yes, it's a trapezium. And the area of a trapezium is half the length, half the sum of the parallel sides times the distance between the parallel sides. Okay, so let's see how I did that. Well, the first one, I get a half. If you look at the height of the first one, you'll see that the first parallel side is a height of 2, and the second parallel side is a height of 4. And I'm just reading those values off the graph. You could substitute the x values into a half x plus 1 to actually work them out and confirm that you get 2 and 4. So a half brackets 2 plus 4 times the distance between them, that's from 2 up to 6, which is 4. Work out that area, you get 6 fours are 24, divide by 2, which is 12. That's very interesting. It's the exact same answer we got for the definite integral from 2 to 6 of a half x plus 1. Precisely. Definite integrals calculate areas enclosed by the curve, the x-axis, and the limits of integration, provided the curve does not cut the x-axis between these values. So now you know what a definite integral gives us geometrically. This is very interesting. Let's continue. Right, let's do an example. So I've called it example 1. Draw y equals x squared minus x and find the definite integral from 2 to 3. All right. This is a quadratic. The y cuts at x equals 0. Okay, so put 0 into that formula. X equals 0, you'll get y equals 0. X cuts go at y equals 0. So you get x squared minus x is 0. Factorize that, and you're going to land up with x equals 0 or 1. And there's my quadratic graph I've drawn. Now I want the definite integral between 2 and 3. So I've drawn those vertical lines at 2 and 3 and shaded that area in. Let's do the integration. I'm going to work out what that area is. Here we go. Integrate x squared minus x. You get x cubed over 3 minus x squared upon 2. And I've got my limits 2 and 3. Now you substitute that 3 into the formula first, and then the 2, subtract the 2 answers, and come back to me. All right, how did it go? Well, if you put the 3 in, you're going to get 3 cubed over 3. That's 27 over 3, which is 9. And then you've got take away 9 over 2. Same goes with the 2. You're going to get 2 cubed over 3, which is 8 over 3. Work out each of those brackets using your calculator and subtract the 2 answers. The first bracket is 4.5. The second one's 2/3. Subtract that. That area is 3 and 5/6. Right. I hope you got that. So let's summarize. In general, the definite integral of f of x dx between a and limits a and b is a new formula, capital F of x, that's the integral of fx, and I'm going to substitute b and a into it. I put a and b on those square brackets. Substitute the b in, you get f of b. Substitute the a in, you get f of a. And there's like a pictorial, general picture of it on the right-hand side there. It represents that area. It's the area caught between the function, the curve y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. Right, here's y equals x squared minus x again, example 2. Find the integral from 0 to 1 of x squared minus x. So the same integral, don't have to change it. Again, I'm going to get x cubed over 3 minus x squared upon 2. But if you look at that area, you'll see that it's below the curve. Okay, so I'm going to do that little piece that's caught between the curve. Caught between the x-axis and the curve. Okay. And it's also between the x cuts 0 and 1. So I'll simply integrate between 0 and 1. All right, substitute the 1 in, you get 1/3 minus 1/2. Substitute the 0 in, you get 0 minus 0. And subtract 1/3, take away 1/2, you get minus 6. That area below the x-axis is always a negative value. So this happens for areas below the x-axis. The result is negative. It is something we must keep in mind. So it is very important to have a sketch when finding areas. So for example, look at this example here. I've just got a general curve there. If I integrate it from A to C, all the way from A to C, okay, you can draw vertical lines at A and C if you like, but they cut exactly on the x-axis. That'll give us the difference between the areas A and B, and that would be called the net area. It actually does area A subtract area B. If you wanted the total area of A and B, you would have to be very careful. You would integrate from A to B, the function f of x, and then you'd add the integral from B to C of f of x, which is going to be a negative answer, so I can put absolute value signs around it, which will create the positive answer. All right. Or another clever way to do it is to integrate B's areas back to front, and that will give you a positive answer. Instead of integrating from B to C, putting the B on the bottom and the C on the top of the integral sign, you put the C on the bottom and the B on the top, and that subtraction will make it positive. I hope you understand that. That'll be f of b minus f of c, and now the area will be positive. So you could have added the area A to the area B like that, where you do the second integral back to front. All right, look at y equals x cubed minus x, example 3. There it is there. It's lovely. It looks very similar to what I've just done. Okay. The x cuts occur where y equals 0. X cubed minus x becomes 0. Factorize that, you get x squared minus 1 equals 0. X squared minus 1 is the difference of two squares. X bracket x plus 1, x minus 1 equals 0. So my 3x cuts are at 0, minus 1, and 1. And I've drawn the graph accordingly. Now I want area A plus B. Area A is easy enough. I'm going to integrate from minus 1 to 0, x cubed minus x. For area B, it goes below the x-axis, so I'm going to integrate backwards, and I've indicated that. Instead of integrating from 0 to 1, I'll integrate from 1 to 0. Okay, see if you can follow it through. Try the example, see if you can get the right answer. Come back to me. All right, I've done the integral there. The integral of x cubed minus x is x to the 4th over 4, and integral of x is x squared upon 2. Okay, and if you're going to substitute the values minus 1 and 0, you're first going to put the 0 in. That gives you 0. Then you're going to put the minus 1 in. That's going to give you minus 1 to the power 4. I'll just discuss a couple with you. That's plus 1 over 4. And if you put the minus 1 into x squared, you get plus 1 over 2. So you get a quarter minus a half there. All right. And then for the second part, where you've got to integrate between 1 and 0, x to the 4th. Okay, putting the 0 in first, you get the zeros. And again, putting 1 in, you get exactly the same as I got, a quarter minus a half. All right, so you land up with those zeros not producing anything, and you get a quarter plus a quarter, which is a half. Now, did you get that? I hope so. Right, now how do we find the area between two curves? All right. Some of them go above the x-axis, some of them go below the x-axis. Some of them meet below the x-axis, meet above the x-axis. What can we do about this? Take a look at that picture there. I've got the curve y equals f of x, which looks like a quadratic. And then I've got a line y equals g of x, a straight line. Okay, make sure you're happy seeing both those curves. Now I want the area A, which is caught between those two curves. The area A starts where they first intersect, and let's say that x value where they first intersect is A. And the second one where they intersect further along on the positive side is B. Now here's all you need to do. Okay, here's the way to go about it. Firstly, to get A and B, you will have to solve the two equations simultaneously. So you'd put f of x equals g of x and solve that to find x equals A and x equals B. Now, to do the actual area, just check which graph is above the other in that interval AB. And if the intervals, they crisscross a couple of times, you just got to check which graph is above the other one. The graph that's on top is going to go first in a subtraction of the two formulas of the functions to be integrated. So here I'm going to find f of x take away g of x, because f of x is the graph that's above g of x between those values a and b. Make sure you're happy that the parabola is above the straight line between those two values a and b. So the actual area is found by integrating between a and b, f of x minus g of x. And you would actually work out what f of x minus g of x is algebraically. Okay. Even if the curves go below the x-axis, this will still sort out all those movements. Okay, so now we're going to try an example. Right, there we have it. Find the area between f of x equals x squared minus 4 and g of x equals minus x minus 2. Okay. Well, x squared minus 4 is quite easy to draw. It cuts the x-axis at minus 4, and then you have your x squared shape. It's simply the graph of x squared pushed down to minus 4. And you should know how to draw the straight line graph of y equals minus x minus 2. It cuts the y-axis at minus 2, and it's got a gradient of minus 1. All right. Now the two graphs cross where the formulas equal each other. So I'll put x squared minus 4 equals minus x minus 2. Bring everything to the left-hand side, you get x squared plus x minus 2 equals 0. Factorize, x plus 2x minus 1 equals 0. Solve that, you get x equals minus 2 and x equals 1. Now make sure you're happy with all that algebraically. So, where I've got little a there on the graph, that's going to be x equals 1. Okay. And the other one is at x equals minus 2. It's actually on the x-axis where they cross as well. Now, which curve is above which between minus 2 and 1? Yes, the line, which I've called g of x, is above f of x between those two limits in the interval minus 2, 1. So, you are going to put the minus 2 on the bottom and the 1 on the top. I'm going to integrate from minus 2 to 1. And you are going to put the straight line curve first, minus x minus 2, take away the quadratic second. Remove those brackets, you'll land up with minus x squared minus x plus 2. That's the function I integrate. Check how I've done it. Come back to me. Okay, the integral of minus x squared is minus x cubed upon 3. And of course, minus x squared upon 2 is the integral of minus x, and then you get plus 2x. Substitute the value 1 in that, easy enough, minus a third, minus a half, plus 2. Just write down the coefficients. And then put the minus 2 in. Be very careful. If you're going to put that minus 2 in place of the x cubed, you're going to get minus 8, and then you've got a minus sign outside it, which changes it back to plus 8. Okay, and the rest should be okay, but it's probably a good idea just to put that into your calculator. All right, now make sure you get the right values here. It's very easy to make mistakes on definite integrals. You land up with 4.5. Okay, so I hope you're happy with now doing areas between curves, areas under curves, and realizing where they're positive and where they're negative, and also what a definite integral is. Nice to speak to you. See you soon. Bye.